Are we starting? It says we're starting. Are we actually started? Maybe. Are we live? It says we're live. I don't see it over here. Are we here? Yeah, we are live. Sweet. Okay. I don't understand why it doesn't show up. And live chat is unavailable. Would be great if somebody would tell me what I need to be doing. Manage. This one. It does not say. No, it is running. Okay, yay. Sorry for the confusion. My confusion. So today, of course, we're going to take requests, but in the absence of requests, I want to get to a new idea I had. I was just thinking the other day about robot navigation algorithms, or more specifically, obstacle avoidance algorithms. Excuse me. Now, most of the time, hobby robotics involves avoiding obstacles, and that's pretty much it. So you have a robot in a room, and it's got some sensors, and its goal is to not run into things. But normally it doesn't have the goal to go from here to there. So I had the idea, what if you put a robot in a room, so we're going to use red for a robot, and we'll use white for the walls, and obstacles. And so you've got something there, you've got something here. You've got all of that, opening and that. And you got something over here. Now, let's suppose that you, as the robot in red, want to get over here. Stop that. You want to get over here. Now, you want to get over there and you want to not run into things. That should be fairly obvious. Let's suppose, for the sake, or to get a best case scenario for this algorithm that I have in my head, that you have a LiDAR. Or you just have multiple sensors all the way around in a circle. It doesn't have to be a LiDAR. But say you can see a point here. Why is... I think I need to adjust a thing. This one. Yeah, don't do that. Okay. Sorry, my pen was bothering me. Suppose you've got a sensor reading there, a sensor reading there. A sensor reading there. A sensor reading there. Another one there. Maybe one way over here. Another one there. Here, 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 here. I'm trying to space them, you know, somewhat evenly. It's not ideal. But the idea is just to give you the concept. And we'll put another one up here just for good measure. Okay. So suppose you've got all of these readings. And you know you want to steer away from the readings. So a robot that was programmed to steer away from the closest obstacles is going to steer this way, right? Because that's the longest distance. Or maybe this way or that way. But we want it to come here. Hang on just a second. Okay, sorry about that. So, we want to steer away from all of the points because that means we're not going to run into stuff, right? But we also want this guy to go towards the goal point. So now we're going to abstract ourselves a little bit from this robot in a room situation and think about it in different terms. So I'm actually going to create a new page just so that we don't have that distracting us. So now let's create a new environment. We're going to use something that you can relate to think about the algorithm that I'm proposing. Suppose this is a pond or pool. It's rectangular, maybe it's a pool. And you've got a rubber duck. This is not a very good rubber duck. Got a rubber duck. And this rubber duck is in a pool of water. And in this pool of water, we have fountains that are spitting water out of them. You got water going that way and that way. You've got fountains here. If the pattern I'm doing looks a little familiar, it's because I'm trying to kind of replicate it from the other page. And if you think about a fountain in a pool of water, there's kind of a field flowing away from it. So you've got ripples that push things away from the source of the water. But let's also suppose that we have a drain that's pulling water into it. And go back to add a couple of more of these fountains. That's probably getting close to being enough, just for the sake of this discussion. So now, these fields obviously reach further than what I've drawn them, because if you have one fountain in a pond, you get ripples all the way to the edge of the pond. But the closer you are to the source of the ripples, or the source of the water, the fountain, the more that water pushes on you. So these things close to the rubber duck are going to push more than the rubber duck, right? And the things further away, like one of these, isn't going to push hardly at all on the duck, especially compared to these. Now the drain applies a global pull. So all of the water wants to go towards the drain, including the water where the rubber duck is. And that's kind of what we're going to try and do with this guy. All of these points are going to act like fountains. They're going to push him away. And this goal, the target, is going to act like the drain. And it's going to try and pull the rubber duck towards the drain. So my proposition is, everywhere we have one of these blue points, so this is a measurement, point. And since it's from a LiDAR or pseudo-LiDAR, something simulating multiple points all the way around in some pattern, we know the angle. So this has an angle. Angle is known. And the distance is known. So theta, angle, distance, both known. And what I want to do is I want to fix a Gaussian distribution around each point. So if this is the point, then I want to have some parameter to control the spread which is the standard deviation, and I want another parameter to control the height, and we'll call that A for amplitude. So I don't remember the formula off the top of my head, and if I was a little more prepared, I probably would have grabbed that. But I don't. I wasn't. So I'll look it up. Distribution function. So we have the Gaussian distribution. This guy is f of x equals 1 divided by the square root of 2 pi sigma squared times e to the negative x minus a, and that's actually the mean, so I'm going to use mu squared over 2 sigma squared. Now that's without this alpha parameter. So I'm going to go back in and erase where I have sigma and turn it into yellow so that you know it's the same thing. Sigma, sigma. This mu I actually want to be 0. And I'm going to change colors for that one too. Mu. I want mu to be 0 for reasons that we'll see in a minute. Which gives us f of x 1 divided by 2 pi sigma squared, and that's square root e to the negative x squared over 2 sigma squared sigma and that guy squared. Now the value, I'll back up. So this is the center where the measurement point was taken. And somewhere out here is D. So this is our robot. Now this red corresponds to this red. Robot. This guy is a robot. Right? And we know this is D because this is the distance from the measurement point. If this is the measurement point, we put our robot out here somewhere. That's the distance. And this way, it kind of models what our fountain's going to be doing. So if we're close to the measurement point, then we have a high number, a larger magnitude number. If we're far away from the measurement point, we have a lower magnitude number, smaller magnitude. And so we're going to use this number, this f of d. So f of d, and I'm not done because I haven't added this amplitude term yet. But f of d is going to be equal to the weight that we're going to use to weight a direction. So one divided by 2, or square root of 2 pi sigma squared times e to the negative d squared divided by 2 negative d squared over 2 sigma squared. And we want this peak magnitude to be A. So A is some number that we're assigning it, but we want f of 0 to be A. So A equals 1 divided by square root of 2 pi sigma squared times e to the 0. Now that's e to the 0 is just 1. So we're going to have A equals hang on. am confusion. We need to insert a term. Blech. B. So it's going to be B times this whole thing. So we're going to have B there. And now we want to solve for B. Square root of 2 pi sigma squared. So then B equals A times the square root of 2 pi sigma squared. So now I can put in A and I'll get B. But if I do that, then I have f of d equals A times the square root of 2 pi sigma squared divided by the square root of 2 pi sigma squared times e to the negative t squared over 2 sigma squared. That cancels with that, and you're left with... Is this correct? Yes. You're left with a e to the negative d over 2 sigma squared, which is mighty fine. Okay. Now that's going to be the weight. This right here, f of d, is going to be the weight applied to the direction of motion of the robot from any given point. But we're not done. This is just the weight. Each one of these also has a direction. So if this guy is number 1 and the robot's facing this way, hang on, that's not pretty. Let's make it look a little nicer. If the robot is facing this way, and this guy is pointing that way, that actually wouldn't be number 1. For convenience, we wouldn't make that 1. We'll call it number n because I don't want to bother counting them all. But this has some angle, theta, and this is probably negative theta, since normally we would measure theta this way, but that's beside the point. We'll call this negative theta. So n that's negative theta. This is positive theta. Okay. Before I get too far, I'm going to double check that my audio is working. Seems to be. Okay, very good. So measurement n has an angle, theta, which means its pointing vector is some cosine theta. And now remember, we're thinking in terms of the robot's coordinate system. We don't care about the global coordinate system. So this red angle is angle 0, and that is also let's see, 1, 0. Okay? Because it is along the direction of travel. Whether or not that's the best coordinate system to use, or coordinate convention to use, could be up for debate. That's the one I'm using for now. I may change it later. But if that guy's moving along that vector, and I am measuring the influence of this point on the robot, then my pointing vector from the robot to that measurement point is cosine theta? Yeah, cosine theta. And then sine theta. So the angle theta leads to a pointing vector, and that needs to be a v hat of cosine theta, sine theta. And the distance leads to a weight of a e to the negative d over 2 sigma squared. Now, we want to add up I'm going to make it bigger because I can. We're going to add up for all n hang on. For all I in 0 to n, because we are mathematicians here. We're mathematicians and computer scientists, so we 0 indexed. Equals 0 to n. That's better. We will add up all of the weights times the vectors and divide by n. And that's going to be vector prime Now, why are we doing this? We're going to use a principle called superposition. And what does that mean? It means we're going to sum up all of the forces, it's not a real force, but all of the simulated forces along each vector from every point. And when we sum them all up, this guy is weighted more then this guy, these two are weighted more than both of those. We will get a weighted direction vector that in this case will point opposite the direction we want to go. So if I'm close to it, I'm going to have a high number. So hang on. Yes. The way it's set up right now, this guy is going to have a larger number. Than one of these others. And I multiply that by the vector to it, it's going to want to go toward it. So what I want to do is negative that. So now this guy will want to push me away, which is what we want. But now I need to add a term. So plus the vector from, or the vector towards the goal. And that's going to be goal. Yeah. Hang on. X, Y, and this guy is going to be X, R, Y, R. And I need to probably put G's on these. Goal, Y, goal. And this is just going to contribute to the whole thing. XG minus XR. Yeah. And YG minus G minus YR. This term, so back up. This term, avoid obstacles. This term, move toward goal or waypoint. There's another term that we can add that will probably help balance some things out, and that's a momentum term, but that won't be on this vector. I'll have to do this, find this vector, and then apply the momentum term to a history of these vectors. And I'm trying to think if this is enough to just do it now, to plug this into my simulator. I want to write out the full formula for V first, though. So V vector. Oh, yeah. There actually is another step. But I'll actually have to write this. So this vector equals negative 1 over n times the sum over all I equal to 0 and to n, and this needs to be it and this will be a times negative dn over 2 sigma squared. Times cosine theta n sine theta n. And I'm going to put all of that in parentheses, plus xg minus xr yg minus yr. And that will give me the vector, not unit vector, that I should try and push the robot along. I think. Is that correct? This may work. If this does not work, then there's a variant on this that we need to do. This should work, though. Yeah, this should work. The variant on this, if you're wondering, is potentially to use the derivative of the Gaussian function instead of the full Gaussian function. And the reason we would use the derivative is because then it's a true gradient descent problem. This is still technically a true gradient descent problem. It's just that I'm starting from my gradient function, not my map function. So I'm using this, using the Gaussian as the gradient of whatever it is that I care about. Or the gradient of my environment. And this is actually not as bad as I expected it to be, for the record. I expected that to be a lot messier. I think doing that will now let me move over to PyCharm. Is that the correct window for PyCharm? Yes, it is. Okay. One moment. Okay, so just a second. This was a very bare bones test to make sure the simulator works, and just for your benefit, let's hide that, and that, and you should be able to see it all if I do this. Boom. Ta-da! Robot spinning in a circle. Very, very basic algorithm. Actually, not really even an algorithm. It's just kind of doing its thing, just to test and prove that it works. If you're curious, we talked about how I made that simulator in some of my previous live streams. Woohoo! Go check them out. When I get this in a polished enough state where I'm not embarrassed to release it, I'll probably put it on a GitHub and put the link in the description somewhere. But until then, it's just going to live here for now. Now, I can get rid of this. Get rid of all of that. I want to set this aside for the moment. We'll get into writing some code. Now, the first thing we want to do is take measurements, right? And actually, I'll go through this so that you know what's going on. So the first thing we do is we open, my config file. And my config file is this guy. And he says, my environment is this config file. And here I just draw a rectangle, which goes around the entire room. I have some walls. I have an ellipse. And that's the shapes that you saw. I give it a title. And so I'll change the title if you remember. I have example simulation. I change this. This turns into gradient descent algorithm. Frame capped at 60 FPS because I don't really care for more than that, and my size is 1024 by 1024. Now, if I run it again, and it's called gradient descent algorithm. And the robot doesn't move because there's no code to make the robot move. But what we do have is something saying take readings on sensor 0. What is sensor 0? It is the robot add sensor is a LiDAR sensor with 0 offset, so it's centered at the middle of the robot. It takes 180 readings in a circle. I'm going to change, I'll leave it. Field of view is a full circle, 2 pi. Minimum range is 1, so anything closer than 1 pixel away, or unit, whatever the units are. It doesn't see anything further than 300 units. It doesn't see. And that's important to note because I need to filter those out for this algorithm to work the way I want it to. So what we're going to do is we're going to say, let's create a function. Def measurement weight, and we're going to take a distance, and we're going to take a default a and a default, and we'll say a is equal to 1, and a default sigma equal to 30, 50. We'll set it to 50. And I'm quite sure that those numbers will have to change, but they'll start there for now. Should I do it this way? I should not do it this way. I should change this from D to distances. Yes. Now, this will give us, we want this to return weights for all of the distance measurements that it takes. So then it's going to be weights equals, and then we're going to apply that function, and that will be a times exponent, so e to the negative distances, squared, divided by 2 times sigma squared. Not Simga, Sigma. Right? If I go back and check my open board, F is A times E. Oh, is D supposed to be squared? D is supposed to be squared. I have neglected to put a 2 on that. That needs to be squared. Squared. You get squared. Squared. Yeah, that's fine. Okay, now we're good. Hide that again. And go back to this one. So now we have the weights. So what I can do is I can say W equals measurement weights evaluated on readings. And I'll leave those defaults for now. Now I have the weights, I need to sum over the vectors. Now what I gotta do is convert my vectors, or convert my measurement indices into pointing vectors. Now, I know how I wrote this LiDAR function to work, and so I will use that to my advantage. So I have resolution, which is the number of elements in W. And actually, we'll just print w.shape, just so that you can see. Oh. Uh-oh. Is W not a thingy? It should be. Type W. That is a none type. Why is it a none type? Okay, I have a problem. Oh. Return weights. There we go. It's a NumPy array. W.shape. 180. So that's 180. Resolution is 180. That's because of how I wrote it. The resolution is the number of elements in the array. Makes sense, I hope. But it's also spread across a field of view of 2 times pi. Well, that's a full circle. So what we're going to do is we're going to say theta equals self.sensors 0.fov sensors, is that an exposed? It is. Okay, good. Here we go. I couldn't remember if it was FOV underscore FOV or just plain old FOV. So it's going to be self.sensors.fov divided by, and I could do the number of elements in W, but I'm not going to do that. I'm going to do self.sensors0.res, and I assume I put that in there too. Readings. Nope. Heh. Okay. Guess what, guys? I'm going to use w.shape0, or probably readings. Even though they're the same shape, just out of principle, I think it's better to do it that way. Now that will only, this, whoa, hello. This only gives me the increment in angles, and so I'm gonna do np dot linspace. You know what? It's better to do it this way anyway. Linspace from 0 to np dot, or 2 times np dot pi, or better yet, self dot sensors FOV readings dot shape 0. So this will give me, thank you. This will give me an array, a NumPy array, with the same number of elements as readings, and W by extension, that's spread from 0 to field of view. Which does make an assumption about how the sensor is oriented, but I am okay with this because I built the robot, supposedly, and this is how I wanted it to behave. Ideally, I wouldn't recalculate this every time because that's never going to change. You know what? We'll do this. Def init args super dot init args, and then I want to append to this, wait, and that needs to be 2. Nope. How are you supposed to do this? You know what? I don't know. I think that's correct. I may have to change that in a minute. But what we want to do is, oh no, I can't do that either. Never mind. Fine. For the time being, we will calculate it every time, just because it makes our lives easier. V equals, and this is actually V prime, but I'm just going to call it V because I want to. It's easier than typing V prime every time. So V is going to be equal to np.sum of, wait, vex. We're going to create one called vex, vectors, and that's going to be equal to np dot array of np dot cosine theta np dot sine theta. And we're going to print vex dot shape. Two by 180 is fine with me. Yes, that's fine with me. And now is that okay? Because now I'm having to deal with shapes. Yeah, it's fine. Yeah. Okay. So that's that. And then we're going to do v equals np.sum of all of the vectors times the weights, and I'm actually going to have to do a tweak because right now our vectors is 2 by the number of, or 2 by resolution, and weights is 1 by resolution, and so I need to make weights match the shape by tiling it along that first axis. So if I do np dot a import numpy as np, a equals np dot range 10, a dot shape, a equals a dot no dot reshape 1 by 10. And I think if you do -1, it'll infer the other dimension. Yeah, see? Potential noise hazard. Nope, never mind. Not going to work. All right. Yeah. Go away. Stop that. I want this one. Now. Yeah, I think I want to do a dot tile or np dot tile a. 1 0. Not tile, repeat. Repeat. I want this to be twice along axis 0. Yeah, that's what I want. So np dot repeat, and this is just going to make it repeat itself along whichever axis I give. Twice along axis equal to 0. That should work. I actually, yeah, that'll work. And then I want to normalize the resulting vector. Actually, I want to sum along axis equals 1. And then I want to do v equals v divided by np dot lineage dot norm of v. So I make it scaled 0 to 1. And now I need another parameter. We'll call this p equals 5, just arbitrarily, times p. P. Yeah. No. I don't need P. Yes. So now V is the vector that points in the direction that I want to travel. And what do I want to do now? That's my travel vector. So that gives me my travel vector. Now I just need to actually move the robot. So I did say this isn't a fully fleshed out simulator. Right now it does not do collision. The other thing it does not have is a move the robot function. So I'm going to move it manually and rotate the robot manually. So data equals np dot tangent? No. A tan 2 arc tan 2. This is going to be V0 V1. This will be self dot heading. Add the angle. I think that's probably right. It may be backwards. Yep, I think it is backwards. I'll go ahead and change that. And then we're going to do self dot x robot. Okay. X. Yeah. Plus equals self dot speed times, and the self dot speed is why I didn't need P. Self dot speed times V0 self dot y self dot speed 1. Yes. And I think this will work. So let's give this a go. Oh boy, I have an angle goofy somewhere. Set the speed to 1. Maybe that is supposed to be a 0. And that's supposed to be a 1. And have I... Yeah, you can't see. Whoa, Nelly. That's definitely not right. One. 0. Well, just so that you can see what it's doing, it's not correct. But it is moving. Let's increase the speed a little bit. Sliding along. Interesting. So there's a bug here somewhere. Let's print out. So let's print V. I'm getting lots of very large, well, one and very small number. Oh, you know what? We forgot to do a thing. And I thought about this, and then I forgot to do anything about it. Let's see. Okay, so problem number one, I didn't filter out the max distance points. So that's a problem. And we can fix that pretty easy, I think. RMV ID C indices equals read. Yeah, readings less than or great. So this would be keep indices. Is anywhere where the readings is less than 300, but I want to give it some buffer, so I'll say 290. Okay. So I will keep those readings. Yeah. And then I'm going to filter these down so that I only have the correct ones of those left. And then the rest of that should be fine. So let's also print len w. Yeah, so you can see we're having numbers. I'm pointing at my screen, you can't see it really, but this number is changing. Sometimes it's more, sometimes it's less. It's not correct. Well, I mean, it is correct, but it's still not behaving quite right. And I'm not entirely sure why. We'll have to look at what W is. So let's print W. That's enough data, I think. So if we look at this, we've got roughly 1 100th, 1 100th, 1 100th, 1 100th, 1 1000th. Okay. So trend, all of these numbers are very small, and some of them are super duper small. So we need to increase A. So we'll make A 100, just because all of those numbers are small. Typically on the range of hundredths. Still small. That one's 1, 1, 1, 1-ish. Close to 1 and descending, and then tiny, and close to 1 again. Which makes sense, right? Because it's going to wrap back around. So numbers up straight forward are going to be one thing, and then as you go further and further away from that, it's going to change. but it should be a pretty much continuous graph. That makes sense to me. And the numbers in the scale that I expect. So let's go back to printing our vector. Same results. Okay, so let's increase the spread of these. We'll change that to 500 as well. Oh, now it's trying to do more things. It's kind of trying. Mostly not, though. Maybe we're not calculating these vex correctly. Print vex. Times 180 divided by np dot pi. Oh, interesting. Because that is a larger number than... No, that's fine. $52 degrees. And that's odd. Okay. Oh. That's because that's not what I... Yeah, okay. For the sake of display, I want to swap these axes. Stop. Okay, so we're going to point... That should end up going back around to 1. Okay. That is also not correct because I need a range. Or can I exclude the endpoint? I might be able to exclude the endpoint. NumPy linspace exclude end. Okay. Linspace endpoint equals false. That won't fix it, but that won't fix my bigger problem, but that'll fix part of it. Yeah. So that's a half. Switch directions. Okay, yeah, and then so that's very close to 1, somewhere in there. Yeah, and we crossed over. Yeah, okay. Okay, so I'm cool with this. The other thing is, this vector that it's come up with is relative to the heading. So what I need to do is add plus self dot heading. Mm. Okay. Odd. um, you guys are seeing this, right? Yeah. Oh boy. Oh boy. That's fun. Okay, so something's not quite right with my rotation logic. I made a helicopter. Or something. Can I exit this? Yeah, okay. Let's maybe bypass that for now and see if the rest of it works correctly. Okay, so now it's pushing away from the wall. What does it do now? Steers away from those walls. Okay, okay. So if we increase sigma, oh, the other thing we didn't do, set a goal. We'll still increase that. The other, maybe the last thing, we need to do that. Okay. So this should behave more or less like a marble. Oh, interesting. That is so odd that it follows the line there for a little bit. And now it's stuck. That's not supposed to be negative then. Are these backwards? These may be backwards. Nope. Definitely not backwards. Or I'm very indecisive. Nope. So we need to change that back to cosine, that back to sine. I need to work out some bugs, and we need to change these numbers to be bigger. And we need to give it a goal. I need to add collision logic because that's not working. But it does kind of mostly avoid obstacles. I said mostly. Give me a break. avoids the walls. If I do this, does it still behave? Yes. Yes, it does. So I didn't break that earlier. I did some fiddling with some of it, and I thought it might have broken, but it did not. Okay, so that needs to be heading plus that mod two times np dot pi. I can take this out. I don't need that anymore. I can print arctan2 v1 v0. That's not what I'm looking for. If I just do arctan, no, I don't know why that's not working. That should be what I'm looking for. Let's stop adjusting the heading, go back to this. The vector is the same. I should also print at this point, I'm just debugging, trying to figure out why is that not working the way I expect it to. Oh boy, That's a very large number, and I did not expect it to be that large. So I should always be trying to make that number go down. And by the way, this is without a momentum term, which is one that I intend to add at some point. 4, 6, 1, 5. Number that's larger. Why did it get bigger? I don't know. It kind of behaves the way I expect it to, but it also kind of doesn't. But I've been up for quite a while now, and my brain is a little bit fried. So I think I'm going to call it for now, and we'll come back to this maybe next week. I may put some time into it between streams, hopefully make it into something more useful, something that behaves better, and I can update you on what I did. So if you liked this, if this has been interesting at all, or if I've taught you something useful, be sure to leave a like, hit subscribe. Be sure to join my Discord. I have a Discord server where I check it frequently for requests and pleas for help. If you have a homework problem of math or anything that I'm comfortable with helping, pop it in there and I'll see if I can help you with it. I think that's all I have for you today, so come back next week, same-ish time, same place, and I'll see you then.